Hello, I'm Dr. Wu, and this is the second of 3 parts of my review of GCSE number theory. We left off learning about the properties of the set of integers, which we now continue. Now that we have this number line, which can now be regarded as having been formed or generated by identifying a 0 point and a 1 point, and then labelling all other points by the number of shifts of size 1 from 0, we get a clear indication that the numbers are ordered from left to right. This means that we can say not only that 2 is less than 3, a fact we knew instinctively as a group of 2 elements being smaller than a group of 3 elements, but we can say minus 3 is less than minus 2, for example, meaning that minus 3 appears to the left of minus 2 on the number line. As well as indicating the relative status of 2 numbers, the symbol can be used to identify subsets of the numbers. For example, the set of all integers less than 2, written in a funny terse notation which is nevertheless globally understood, is written as the set of things in integers restricted to those things to the left of 2 on the number line, and is shown on the number line as so, and note the hollow circle on the number 2 itself. If we wanted to include 2 in the subset, we would have written the set of things in integers restricted to those things less than or equal to 2, like this, and indicated the fact on the number line with a solid dot at the 2 position. Sometimes we see intervals with 2 endpoints, such as the set of things in integers restricted to 2 being to the left of the things, which are to the left of or equal to 4, and it's this region here on the number line. Similar to less than, we also understand greater than, meaning numbers to the right of some point on the number line. The set of things in integers restricted to the things to the left of 2 and the things to the right of 4 is this disconnected region of the number line. Finally, we may consider the set of all numbers except a particular one. The set of things in integers restricted to the things not equal to 2 includes all the integers except the number 2 and would be indicated on the number line like this. Now for any integers a, b and c, a times b plus c is equal to a times b plus a times c. Note the use of parentheses again to change the order of operations here. Especially note that a times b plus c is not the same thing as a times b plus c with those parentheses in there. The proof is a times b plus c is b plus c added to itself a times by the definition of multiplication, and since addition is associative we can rearrange this so that it's b added to itself a times plus c added to itself a times, and this is a times b plus a times c using the definition of multiplication. Informally, we can consider the expression 3 times 2 plus 3, which, according to the theorem, is the same as 3 times 2 plus 3 times 3. We can see this by drawing out a 3 by 2 rectangle and a 3 by 3 one like this. We see then that the sum of the 2 rectangles has the same area as a 3 by 5 rectangle as expected. We could have done this with any integers, not just 2, 3 and 3, and so it is a quite general proof, albeit an informal one. As practice in writing and proving formal mathematical theory, the above theorem can easily be extended into a 3-way summation. A times b plus c plus d is a times b plus a times c plus a times d. We use associativity of addition to write it like this. And we use distributivity of multiplication over addition once to get to this. And then applying it to this second term again, we finally arrive at AB plus AC plus AD as required. Now that we've extended the number system from an additive point of view, we must work out how all the new numbers work with multiplication. Now, we get that a times minus b means adding minus b to 0 a times, which is the same as subtracting b from 0 a times, and so we see clearly by considering the situation on the number line that a times minus b is just the same thing as the negative of a times plus b. Now consider 0 times b, which is a minus a times b, because anything less itself is 0. And that's just a plus minus a times b. And by distributivity, that's a times b plus minus a times b. And that's a times b minus a times b. And that is in fact 0. So this tells us that 0 multiplied by anything is 0. Now consider again that 0 is equal to 0 times minus b, because we've just shown that 0 times anything is 0. And this is a minus a times minus b. Anything minus itself is 0. This is a plus minus a times minus b. A times minus b plus minus a times minus b, which is minus a times minus b plus a times minus b, is minus a times minus b minus a times b. And remember that this is 0, so we must have that these two things that we're subtracting from each other must be the same, i.e. minus a times minus b is plus a times plus b. And we see that the meaning of multiplying negative numbers together is the same result as multiplying the corresponding positives. Now, returning to the theme of turning ideas on their heads, we now look to define the opposite or inverse of multiplication. A equals b divided by c if and only if b equals ac. Note that division is often written within lines of text with a solidus, and sometimes, especially in very elementary maths books written in English, with the divide sign here, known as the division symbol. This is not globally recognised and in fact is rarely seen outside of elementary school. Again, see how we are being very abstract here. We don't talk about that if you share 6 apples between 3 children, they would get 2 each. That's because we're not teaching the subject of numbers here, but we're reviewing the underlying theory. Some might say that we are casting the ideas into a more rigorous framework. Now we can write that 6 divided by 3 equals 2, because we already know that 6 equals 2 times 3. By the way, note how we have to put the multiplication cross in here, otherwise it would look totally wrong. 6 equals 23? No. And hereby we come across a new problem. What is the answer to 7 divided by 2? We seek the solution of 2 times something is equal to 7. And looking at the number line, we see that the answer is this point, which is halfway between the point labelled 3 and the point labelled 4. A similar problem is 2x equals 1, with the symbolic answer there that x is 1 over 2. This is precisely the label we use to denote the point halfway between 0 and 1. This point has come to be called the half, and we also recognise the special points, a third and a quarter along the line from 0 to 1, and these are of course symbolically written 1 over 3 and 1 over 4. The point halfway between 3 and 4 would logically be called 3 plus 1 over 2, but we write 3.5 like this for brevity. In general, a point between 0 and 1 may be identified by dividing the whole interval into some appropriate number and then counting the number of such subdivisions between 0 and our point of interest. For example, dividing the interval into 7, we see that 1 7 would be here and 3 7s here. In doing this, we clearly see, for example, that 3 7s is just 3 lots of 1 7. And in general, therefore, that any x over y is x times 1 over y. That's just substituting symbols for those numbers. The term 1 over y is called the reciprocal of y, and so we see that division by a number is the same as multiplying by the reciprocal of that number. Compare it with the fact that subtracting is the same as adding the negative of a number. Now note how AB over CD is A times B times 1 over C times 1 over D. It's A times 1 over C times B times 1 over D. It's A over C times B over D. This informs us that 1 over minus A is 1 times 1 over minus A, because 1 times anything just leaves itself unchanged. And that's minus 1 over minus 1 times 1 over minus A, because anything divided by itself is just 1. And that is minus 1 times 1 divided by minus 1 times minus A, which is just minus 1 divided by plus A. This shows us that divisions involving negatives works the same way that multiplication does. Those involving a positive and a negative produce a negative answer, and those with 2 negatives produce a positive answer. For example, minus 2 divided by minus 3 is minus 2 times 1 over minus 3. Minus 2 times minus 1/3 is plus 2 times plus 1/3 is 2/3. Also see that x plus y over 2 is a half x plus y, is a half x plus a half y, is x over 2 plus y over 2. And so we have seen how the space between 0 and 1 can be populated quite haphazardly with fractions. But we can also divide this interval up, and by implications all other unit intervals along the line, more systematically. We start by dividing it into 10 equal increments and use the 10 symbols we have to denote each one. And then we can take each such 1/10th interval, subdivide that into 10 smaller intervals, of which there are 100 in the entire unit interval, and give each of those a symbol. We address any point on the line by the integer on the side closest to 0, followed by a decimal point, followed by the tens position, then the hundredths, etc. So for example, this point here is 0.76, meaning literally that after point 0 on the number line, it is then 7/10 further along and then another 6/100ths. At this point, you will be forgiven for thinking that every point can be addressed this way, by going down enough interval sizes to be able to pinpoint each place on the number line. But you'd be wrong. There are points on the number line at which the process of subdividing by 10 to get higher accuracy never ends, and you never get a decimal number which fully locates that point with perfect precision. These strange little animals are called irrational numbers, and conversely, all numbers which can be exactly expressed as some fraction of finite parts are called rational numbers. An old-fashioned name for a fraction is quotient, and so the set of all rational numbers is called Q. All of the points on the number line, including the irrational ones as well as the rational ones, make up a set called the real numbers for somewhat comical reasons outside the scope of this work. They are labelled with the letter R. Again, most textbooks use highly stylised versions of these symbols. As a point of clarification, note that not all infinite decimals are irrational. The number 1/9 has got the decimal representation 0.11111111, etc. ad infinitum. The number 1 over 99 has the representation 0.0101010101 ad infinitum. And 1 over 999 is 0.001001001001 ad infinitum. The number 942 over 999 is 0.942942942942942942, etc., etc., ad infinitum. And so we see that any recurring decimal can be converted to a fraction following this pattern. Hence, recurring decimals represent rational numbers. It's only decimals without any recurring patterns in them that are irrational. As a matter of notation, we write a times a equals a to the power of 2, also spoken as a squared, and more generally we have exponentiation. A to the n means a multiplied by itself n times. Now, a to the power b times a to the power c is a to the power b plus c. And we see this just by writing it all out. A to the b times a to the c is a multiplied by itself b times, multiplied by a multiplied by itself c times. So altogether we're multiplying a by itself b plus c times, and that by definition is a to the power of b plus c. A to the power of b to the power of c is equal to a to the power of b times c. Again, we write this all out. So this is a multiplied by itself b times, and then that entire pattern is repeated c times, so that the total number of times we're multiplying a by itself is c lots of b, which is b times c. Now we need a to the power of 0 to be equal to 1. Consider a to the power of 0 times a to the 2. This can be expanded as a to the 0 plus 2, which is a to the 2, which is 1 times a to the 2, and we see then that comparing the start and the end of this chain of equivalences, that we must have a to the 0 is 1 to make the original expression evaluate to the same thing as the final one. It should be clear also that a to the 1 is just a. And now we note that as a to the 0 is a to the n minus n, is a to the n times a to the minus n, and anything to the 0 is 1, so that a to the minus n must be equal to 1 over a to the n. And this informs us of the meaning of negative powers. They are just the reciprocal, i.e. 1 over, of the corresponding positive power. Note now then that we can write x over y is x times 1 over y is x times y to the minus 1. Note again that as a to the power of 1 is a to the power of n over n, is a to the power of n times 1 over n, is a to the power of n to the power of 1 over n, and this is just a, because anything to the power of 1 is just itself. Then the act of raising to the 1 over n is to reverse, undo the act of raising to the n. We say technically that raising to 1 over n is the inverse of raising to n. This is known as taking the root. In the special case that n equals 2, a to the 2 is called squaring, it's a squared, and a to the half is called taking the square root of a. Likewise, when n equals 3, a to the 3 is called cubing, it's a cubed, and a to the 1/3 is called taking the cube root. Generally speaking, a to the n is raising a to the power of n, and a to the 1 over n is taking the nth root of a. So for concrete examples, 2 squared is 4, ergo 4 to the half is 2. 3 squared is 9. Root 9 is therefore 3. Now, regarding square numbers, GCSE Maths expects students to know the first 12. So after 4 and 9, which we've just done, we've got 4 fours is 16, 5 times 5 is 25, and then we've got 36, 49, 64, 81, 100, 121, and 144. Having these numbers in your head means that when you see 1, then you can immediately write down the square root, e.g. 64 to the half is 8. You don't generally need to know about cube numbers, but do be aware that 2 to the 3 is 2 times 2 times 2 is 8. So 8 to the third is 2. Now let's think about the value of minus 3 squared. It is minus 3 times minus 3, which is the same thing as plus 3 times plus 3 is 9. But we also had that 3 squared is 9, and this tells us that, going the other way, the square root of 9 is ambiguous, because it could be either plus 3 or minus 3. We symbolically write this down like this, and say that 9 to the half equals plus or minus 3. Note that it's very common to use this sign to denote the positive root of a number. Thus we could have written 9 to the half plus or minus root 9 equals plus or minus 3. See now, 10 to the power of 0, like anything to the 0, is 1. 10 to the 1, like anything to the 1, is just itself, is just 10. 10 to the 2 is 10 times 10 is 100. 10 to the 3 is 10 hundreds is 1,000. And in general, we see that 10 to the n is the number that's 1 followed by n zeros. Also, 10 to the minus 1 is 1 over 10, is 0.1. 10 to the minus 2 is 1 over 10 squared. It's 1 over 10 times 10. It's 1 over 100 is 0.01. 10 to the minus 3 is 0.001, etc. So you see that multiplying by powers of 10 has the effect of moving the decimal place around, inserting zeros where necessary. Positive powers of 10 move the decimal place to the right, and negative powers move it to the left. So in general, a number like 3,450,000 can be written as 354 times 10 to the 4, which is also 34.5 times 10 to the 5, and it's 3.45 times 10 to the 6. Notice how the decimal point moves in the opposite direction to what we just said, because the increasing powers of 10 that we're multiplying by compensate by moving it back to the right. Scientists would usually choose the latter representation, in which the index of 10 is a multiple of 3, corresponding to suffixes like kilo, mega, giga, etc. 4 gigabytes means 4 times 10 to the 9 bytes of computer memory, for example. It should be noted that the GCSE syllabus states that the standard form for 32,000 is 3.2 times 10 to the 4. You've got to put the first part in the range from 0 to 10, or in other words, the decimal point has to appear immediately after the first digit. Given the simple origin of numbers as labels on the sizes of sets of things, it's a surprising fact that there is more structure than them being a simple progression of incrementing by 1. When we multiply numbers together, we get another number, but not all numbers. For example, no multiple of numbers makes up 7, or 11, 13, 17, 19, 23. The list goes on and on forever. Also 2, 3 and 5 are numbers which are not multiples of some other numbers. These numbers, which are literally indivisible, are the atoms of the number world and are called prime numbers. All other numbers are composite numbers, and by definition can be divided into smaller numbers. Those smaller numbers would be either prime or composite, and if the latter, they can be further subdivided until only primes remain. Thus it is seen that all numbers can be considered composed of one or more primes, in the same way that all molecules are composed of one or more atoms, the indivisible units of material things. To cement the idea, we note further that the prime decomposition of any number is unique when the primes are listed from smallest to biggest according to those ordering operations we saw earlier, less than, greater than. To find the prime decomposition of a number, simply divide it down as much as you can. For example, 18 is 2 9s and 9 is 3 3s. Both 2 and 3 are prime numbers, so they can't be further subdivided, and so the full decomposition of 18 is 2 times 3 times 3. Armed with this knowledge, we now see how to systematically determine greatest common divisors of two numbers. The meaning of that will become apparent shortly. We decompose the two numbers into primes, determine the primes which are shared between the two numbers, and multiply them together. We compose those shared primes. The result is the greatest common divisor. A concrete example is the numbers 18 and 24. So 18, we've already seen, is 2 times 3 times 3. And 24, you can verify, is 2 times 2 times 2 times 3. The common primes there are a 2 and a 3. And so the greatest common divisor is 2 times 3 equals 6. So now we can see that 18 is 3 times 6 and 24 is 4 times 6. This is the meaning of common divisors. Both numbers divide by 6 here. As you can see, 6 is the common divisor. This lights the way to the systematic simplification of fractions, because the greatest common divisor is the part which cancels out of heavy fractions. To continue the example, 18 divided by 24 is 3 times 6 over 4 times 6. It's 3 over 4 times 6 over 6 is 3 quarters, because the 6 divides itself away. Now, we have seen that irrational numbers cause problems because they can't be written down. This means that the result of many expressions involving irrational numbers also cannot be written down, which is often the case when square roots are involved. But we try our best to minimise this, and in the case of square roots we can use the prime decomposition to achieve this. For example, consider 12 to the half. This is 2 times 2 times 3 to the half, and that's 2 times 2 to the half times 3 to the half, and that's 2 squared to the half times 3 to the half, and that's just 2 times 3 to the half, and that is plus or minus 2 root 3. So today we'll learn to count and add things together. Starting from 3 intuitive ideas about sets, set sizes and set disjointedness, we've built up a powerful number system and a powerful arithmetic around it. This simple idea has been massively extended. We've learned not just the simple natural numbers, but negatives, decimals, fractions, and even those super mysterious irrational numbers that can't be written down properly. And we've learned to add, subtract, multiply and divide all of these things together. These are the foundations on which all of mathematics is built. Don't underestimate this achievement. It's taken humanity about 5,000 years to get this far. Although we've covered the entire theory of numbers at GCSE level now, we still don't know how to actually work with these things. So the final part of this review trilogy deals with these practicalities. We will pull together all the theoretical results that we've gathered above and see how they actually allow us to systematically compute with numbers in general.